So let's take a look at triple integrals in cylindrical and spherical coordinates. Now starting off with cylindrical coordinates, remember they are always in the form r comma theta comma z. So if we have the triple integral of some multivariable function with three variables, so f of x, y, z, and we're trying to convert the rectangular coordinates into cylindrical coordinates, then inside the triple integral, let's say with the triple integral, remember x equals r cosine theta in cylindrical coordinates. So we have f of r cosine theta, comma, y is going to be r sine theta, and z stays the same. And in cylindrical coordinates, whenever you convert the triple integral, you always have to multiply by the extra r variable, similar to how we converted into polar coordinates with double integrals. Now spherical coordinates are going to be in the form rho comma theta comma phi. And so if we have the triple integral once again of a multivariable function that's in rectangular coordinates, and we want to convert it this time into spherical coordinates, inside the triple integral, well, this one's going to be a long one. Once again, x is going to be equal to rho sine phi cosine theta, so rho sine phi cosine theta, comma y, which is rho sine phi sine of theta, comma z, which is just rho cosine phi. Now, in spherical coordinates, whenever we convert the triple integral, we always need to multiply by rho squared sine phi. Now, keep in mind, we also need to change the bounds of integration. So instead of dv, we'll have something like dr, d theta, and dz for cylindrical coordinates, and then for spherical, instead of dv, we'll have something, I'll just write it up here, like d rho, d theta, and dp. So for these first set of problems, let's go ahead and just evaluate the integral. So for number 1, we have the triple integral from 0 to 4, from 0 to 2 pi, and this time from r to 4, of just r times dz, d theta, dr. So realize that it is already in cylindrical coordinates since we have the variables r, theta, and z. So all we have to do is just evaluate this. So if I write the inside integral from r to 4 of r dz, the integral of r dz is just r times z. We're going from the variables, or the z bounds of r to 4. So we have r times, when I plug in 4 for z, we'll get 4, minus when I plug in r for z, we'll get r. So we're left with 4r minus r squared. Now let's go ahead and evaluate the middle integral from 0 to 2 pi, this time with respect to theta. So 4r minus r squared is just a constant, so the integral is 4r minus r squared all times theta. And we can evaluate from the theta bounds of 0 to 2 pi. So then we'll get 4r minus r squared times, when I plug in 2 pi for 0, or when I plug in 2 pi for theta, we'll get 2 pi, minus when I plug in 0 for theta, we'll get 0. So we're just left with 2 pi times 4r minus r squared. Now let's go ahead and evaluate the outer integral, this time from 0 to 4, with respect to r. Now since the 2 pi is a constant, that can come outside the integral, so we get 2 pi times the integral from 0 to 4 of 4r minus r squared times dr. And so the integral of 4r is going to be 2r squared minus the integral of r squared, which is r cubed over 3. Don't forget we do have 2 pi on the outside. Let's go ahead and evaluate it from the r bounds of 0 to 4. So we get 2 pi times, well, when I plug in 4 for r, we'll get 4 squared 16 times 2 is 32, minus, we get r to the third power, so 4 to the third is 64 over 3, minus, when I plug in 0, we just get 0 minus 0. So that will cancel, and so we're left with 2 pi times 32. I can rewrite it as 96 over 3, so I can match the common denominators. Now 96 minus 64 is 32, so we get 2 pi times 32 over 3, and so that will give us 64 pi over 3 as the final answer. So now for number 2, we have the triple integral from 0 to pi over 6, from 0 to pi over 2, and from 0 to 3 of rho squared sine phi, d rho, d theta, d phi. Now since we have the variables rho, theta, and phi, this tells us that we are in spherical coordinates, so we just have to evaluate now. So if I write the inside integral from 0 to 3 of rho squared times sine of phi d rho, then when I integrate, sine of phi is just a constant, so we get sine of phi times rho cubed over 3. So let's go ahead and evaluate rho from the bounds of 0 to 3. So when I plug in 3 for rho, we'll get sine of phi times 3 cubed is 27, 27 over 3 is a 9, minus when I plug in 0 for rho, I'll just get 0. So we're left with 9 sine of phi. So now let's evaluate the middle integral from 0 to pi over 2 with respect to theta. So the integral of 9 sine of phi with respect to theta, since 9 sine of phi is just a constant, we'll just have 9 sine of phi times theta. Let's go ahead and evaluate from 0 to pi over 2. So we get 9 times sine of phi times, when I plug in pi over 2 for theta, we'll just get pi over 2, minus when I plug in 0, we'll get 0. So then we're left with 9 pi over 2, if I can write that down up here, 9 pi over 2 times sine of phi. So finally, let's evaluate the outer integral from 0 to pi over 6. This time we're going to integrate with respect to phi. So 9 pi over 2 is a constant, so the integral of sine of phi is going to be negative cosine. So we get negative 9 pi over 2 cosine of phi. Let's go ahead and evaluate from 0 to pi over 6. Now we get 9 pi over 2 times, well, we get cosine of pi over 6 minus cosine of 0. Cosine of 0 is 1. So when I simplify, we'll get negative 9 pi over 2 times cosine of pi over 6 is going to be square root of 3 over 2 minus 1. And so in order to simplify even further, I'm just going to go ahead and factor out a 1/2 and bring it outside to multiply by negative 9 pi over 2. So then we'll get negative 9 pi over 4, because that's negative 9 pi over 2 times 1/2, times, if I factor out a 1/2 from inside here, we basically get square root of 3 minus 2. And then I can go ahead and distribute the negative inside the parentheses. So then we'll get the final answer of 9 pi over 4 times 2 minus the square root of 3. So now for these next set of problems, let's go ahead and convert the triple integral first into cylindrical coordinates and then evaluate. So for number 1, we have the triple integral of the square root of x squared plus y squared dv, described by E, where E is the region that lies inside the cylinder, x squared plus y squared equals 16, and between the planes z equals negative 5 and z equals 4. So I can start off by converting what's inside of the square root function here. So we have x squared plus y squared. Now remember that x squared plus y squared equals r squared. And we have the square root, so then the square root of r squared is just going to be r. So if I rewrite the triple integral, we get the triple integral of r. Now remember, whenever we're converting into cylindrical coordinates with triple integrals, we always have to multiply by the extra r variable. So then r times r will give us r squared. So now let's go ahead and find the bounds of integration. So it's telling us here that z ranges from negative 5, where the region is between z equals negative 5 and z equals 4. So we can tell using that information that the z bounds range from negative 5 to 4. Now in order to find the x and y bounds, we need to go ahead and graph the cylinder x squared plus y squared equals 16. So in order to graph this in 3 dimensions, the z variable is missing from that equation, so we know the cylinder is going to be on the z-axis. So if I go ahead and draw a cylinder here, now the radius squared is 16, so that means the radius is going to be 4. I'm just going to draw a cylinder here with a radius of 4. Now remember, cylindrical coordinates are going to be in the form r comma theta comma z. So we've already found the z bounds, and now we need to find the r, or the radius, and the theta bounds. So the radius obviously goes from 0 to 4, so we can obviously write r is between 0 and 4, so those are the bounds. Now let's find theta. So notice all the points in the cylinder go a complete 360 degrees around, which means our theta values range from 0 to 2 pi. So we can say theta is in between 0 and 2 pi. So now we can go ahead and plug those bounds into the triple integral. So you can put them in any order since all the bounds are constants. So let's go ahead and just put the z bounds first. So from negative 5 to 4, I'll put dz. Let's go ahead and put the r bounds next, from 0 to 4, so dr. And then we have from 0 to 2 pi, those are going to be the theta bounds. So I'll put d theta on the very outside. So now I can go ahead and evaluate this triple integral. So writing the inside integral from negative 5 to 4 of r squared dz. Now in this case we're going to integrate with respect to z, so the integral is just going to be r squared times z. Let's go ahead and evaluate from negative 5 to 4. So when I plug in 4 for z, we'll get 4, minus when I plug in negative 5, we'll get negative 5. Minus a negative 5 means plus 5. So then we're left with 9r squared. Now let's go ahead and evaluate the middle integral from 0 to 4 this time with respect to r. So the integral of 9r squared is 9r cubed over 3, or in other words 3r cubed. Let's go ahead and evaluate from the r bounds of 0 to 4. So when I plug in 4 for r, we'll get 3 times 4 cubed is 64, minus 0 cubed is 0. So then we'll get 64 times 3, which will give us 192. Now let's go ahead and integrate or evaluate the outside integral from 0 to 2 pi, this time with respect to theta. Integral of 192 is 192 theta. If we evaluate from 0 to 2 pi, we'll basically get 192 times 2 pi minus 0, or 192 times 2 pi, which will give us 384 pi as the final answer. So now for number 2, let's go ahead and evaluate the triple integral of e to the power of z times dv, described by e, where e is enclosed by the paraboloid z equals 1 plus x squared plus y squared, the cylinder x squared plus y squared equals 5, and the xy plane. So if I convert e to the z into cylindrical coordinates, notice that it's going to remain as e to the z, because since z just remains as z in cylindrical coordinates, we can just leave it as it is. Once again, cylindrical coordinates are in the form r comma theta comma z. So let's go ahead and find all these bounds. So first of all, we know that e is enclosed by the paraboloid, which is in the form z equals some function, and the xy plane. The xy plane, notice, is when z equals 0. So we're basically going from the xy plane all the way up to this function here. So we're going from 0, or the z values, of 0 to 1 plus x squared plus y squared. Now this is cylindrical coordinates, so we need to convert into cylindrical coordinates. So x squared plus y squared once again is going to be r squared. So we can say instead of 1 plus x squared plus y squared, we can say z ranges from 0 to 1 plus r squared. So now in order to find r and theta, let's go ahead and graph the cylinder similar to the previous problem here. So I draw a three-dimensional coordinate system, drawing out a cylinder here. Now the cylinder is just going to have z as the axis of the cylinder, the z-axis, and the radius, well, r squared is 5, so the radius is going to be the square root of 5. In this case, r is going to be the square root of 5. Notice the r ranges from 0 to square root of 5, so I can say that. And since all the points on the cylinder range from 0 to 360 degrees, or 0 to 2 pi radians, then we can say theta goes from 0 to 2 pi. So those are our bounds. Now, since 1 plus r squared is a variable as part of the z bound, let's go ahead and put that first. So, or on the inside integral. So z goes from 0 to 1 plus r squared. So then I'll put dz on the inside. Then I can put either one. Let's go ahead and put r first. 0 to square root of 5 times dr. And then we have theta from 0 to 2 pi. Then I'll put d theta at the very last. Now one last thing, don't forget when converting into cylindrical coordinates and triple integrals, once again we always have to multiply by the r variable. So we have r times e to the z. So let's go ahead and evaluate. So we have the inside integral from 0 to 1 plus r squared of r times e to the z dz. And so if we're integrating with respect to z, the integral of r times e to the z is going to be just r times e to the z. Let's go ahead and evaluate from the z bounds of 0 to 1 plus r squared. So when I plug in 1 plus r squared for z, we get r times e to the 1 plus r squared minus e to the 0, which is 1. So then if I just distribute over the r, we'll get r times e to the 1 plus r squared minus r. So now let's evaluate the middle integral from 0 to the square root of 5 times dr. So we're going to integrate with respect to r. Now the integral of r times e to the 1 plus r squared, in this case I can use simple u substitution. So if u equals 1 plus r squared, then du, if I'm deriving with respect to r, is going to be 2r dr. So then dr, if I isolate, will be du over 2r. So when I go ahead and I'm going to rewrite this integral just separately. So we get the integral of r times e to the 1 plus r squared dr. Now if I use u substitution, we get the integral of r times e to the u times dr, which is du over 2r. The r's will cancel, notice, and the 1/2 can come outside as a constant. So we're left with 1/2 times the integral of e to the u du, which is just 1/2 e to the u. And u once again is 1 plus r squared, so I can substitute that back in. So now we have minus the integral of r, and the integral of r is just minus r squared over 2. So now let's go ahead and evaluate from the r bounds of 0 to square root of 5. So when I plug in square root of 5 for r, we'll get 1/2 e to the 1 plus square root of 5 squared, which is 5. So I can replace that with e to the 6th power minus square root of 5 squared is just 5 over 2. So then we get 5/2 minus when I plug in 0 for r, and we'll just get 1/2 times e to the 1 plus 0 squared, so it's e to the 1st, which is e, minus, and we just get 0. So the 0 I can just cross off, and so we're left with 1/2 times e to the 6th. I'll put the negative 1/2 e next, so minus 1/2 times e, and then we have minus 5/2. Now what I can do here is actually just factor out a 1/2, so then I'll get 1/2 times e to the 6th minus e, and then minus 5. So now we can go ahead and integrate or evaluate the last integral from 0 to 2 pi of d theta, or times d theta here. So this entire thing is a constant, because when we're integrating with respect to theta, the integral will just be 1/2 times e to the 6th minus e minus 5 times theta. So let's go ahead and evaluate from the theta bounds of 0 to 2 pi. So when I evaluate, we'll get 1/2 times e to the 6th minus e minus 5 times, when I plug in 2 pi for theta, we'll get 2 pi, minus when I plug in 0 for theta, we'll just get 0. I can cross out the 0, and so when I multiply these two, the 2's will cancel, and so we're left with pi times e to the 6th minus e minus 5. And that's the final answer. So now for this next set of problems, let's go ahead and convert using spherical coordinates. So for number 1, we have the triple integral of x squared plus y squared plus z squared dv, described by the region B, where B is going to be the unit ball, x squared plus y squared plus z squared is less than or equal to 1. Now if I were to go ahead and draw the unit ball here, in a three-dimensional coordinate system here, we have x squared plus y squared plus z squared is less than or equal to 1. So the unit ball is basically a sphere with its center being at the origin 0, 0, 0, and the radius, or rho, is going to be 1. So rho equals 1. Now once again, spherical coordinates are going to be in the format rho comma theta comma phi. So when we find the bounds of rho, realize that it goes from 0, the center, all the way to 1. So we can say rho ranges from 0 to 1. Now since this is a complete sphere, we can say that the theta values range all the way from 0 to 2 pi. So theta values from 0 to 2 pi. And remember, phi is just going to be, if we pick a point here on the sphere, let's say right here, then phi will just be the angle from the positive z-axis to that point. Now the value of phi can range from 0 to pi, pi being its maximum and 0 being its minimum value. Since this is a complete sphere, the phi boundaries are automatically going to be from 0 to pi. So now let's go ahead and convert x squared plus y squared plus z squared into cylindrical or spherical coordinates. So we can use the simple formula here that x squared plus y squared plus z squared equals rho squared. So I'm going to replace all this with rho squared. And so we get the triple integral of rho squared. Don't forget, when we convert in triple integrals to spherical coordinates, we have to multiply always by rho squared sine phi. So what we're really getting here is rho to the 4th times sine phi. And so let's go ahead and insert our bounds. So let's start with rho here from 0 to 1. So we have d rho. Next one, let's say theta goes from 0 to 2 pi. So d theta, and then d phi is on the very outside, with phi being, or phi ranging from its bounds 0 to pi. So now let's go ahead and evaluate. So we have the inside integral from 0 to 1 of rho to the 4th sine of phi dp, or d rho. Now if you integrate rho to the fourth sine of phi with respect to rho, then sine of phi is just a constant, and the integral of rho to the fourth is rho to the fifth over 5. I'm going to bring the 1/5 and attach it with the sine of phi, so we get sine of phi over 5 as a constant times rho to the fifth. Let's go ahead and evaluate the rho bounds of 0 to 1. So then we get sine of phi over 5 times, when I plug in 1 for rho, we'll get 1 to the fifth, or 1, minus when I plug in 0, we'll get 0. So we're just left with 1/5 times sine of phi. So now let's evaluate the middle integral from 0 to 2 pi with respect to theta. So the integral of that will just be 1/5 sine of phi times theta. We can evaluate from the theta bounds of 0 to 2 pi. So when I evaluate, we'll get 1 over 5 times sine of phi times, when I plug in 2 pi for theta, we'll get 2 pi, and then when I plug in 0, we get minus 0. So then we just get 2 pi over 5 times sine of phi. Let's go ahead and integrate or evaluate the final integral from 0 to pi with respect to phi this time. So 2 pi over 5 is just a constant, and the integral of sine of phi is negative cosine phi. So we have negative 2 pi over 5 times cosine of phi. Let's go ahead and evaluate from the phi bounds of 0 to pi. So when I plug in pi for phi, we'll get negative 2 pi over 5 times cosine of pi, which is negative 1, minus cosine of 0, which is 1. So then we'll get negative 2 pi over 5 times negative 2. Negatives will cancel, and so we're left with 4 pi over 5. And that is the final answer. So now for number 2, we have the triple integral of z dv, described by the region E, where E lies between the spheres x squared plus y squared plus z squared equals 1, and the other one x squared plus y squared plus z squared equals 4 in the first octant. Now remember, in the xy coordinate plane, every section was divided into 4 quadrants, right? So we had quadrant 1, we had 2, we had 3, and then we had 4. Well, in the 3-dimensional coordinate system, we have what's known as octants. So if I were to draw a 3-dimensional graph here, now if the first quadrant is where x and y are positive, then the first octant is where all x, y, and z values are positive. So it's kind of difficult to show this in this kind of view, but it's basically the octant that is facing us right now, where the x, y, and z values, where all 3 of these are going to be positive. Now, before I actually draw the spheres, I'm just going to go ahead and erase the negative x, y, and z axes here, or the negative portion of the axes. So now let's go ahead and draw these spheres. So we have another one of these spheres that has the center at 0, 0, 0, and this time has a radius of 1. So say sphere is at 0, the rho value is going to be equal to 1. Now another sphere is also centered at 0, but this time has a little bit bigger radius. Now be careful, because this is not, the radius is not 4, because x squared plus y squared plus z squared equals rho squared. So in this case, rho is going to be the square root of 4, or 2. So we can say rho in this case is equal to 2. Now we're looking for the region in between the spheres. So we're basically looking for the rho values between 1 and 2. Now, when looking at the theta bounds, realize that this is only taking place in the first octant. So in this case, we start from the positive x-axis, and are basically only going 90 degrees counterclockwise. So this is going to be theta, pi over 2. So we can say that theta values range from 0 to pi over 2. And then for the value of phi, we start from the positive z-axis, and remember, it's only going to be in the first octant, so we cannot go below the xz plane. So we basically stay from 0 to pi over 2 as well, as the angle of phi. So I go ahead and rewrite 0 to pi over 2. So now I can go ahead and rewrite the triple integral. Now, if I convert z into spherical coordinates, remember z is going to equal to rho cosine phi. Remember, when we convert into spherical, we always have to multiply by the extra rho squared sine phi. So what we're left here with is the triple integral of rho cubed cosine phi times sine of phi. Now since all of our bounds are constants, we can go ahead and put whichever one first on the inside. So let's go ahead and put a row first. So row goes from 1 to 2, so we have d row on the inside. Let's put in theta from 0 to pi over 2, so d theta, and then we have d phi lastly, also going from 0 to pi over 2. So now we can go ahead and evaluate. So we have the integral from 1 to 2 of rho cubed times cosine phi times sine of phi. And we're going to integrate with respect to rho. So in this case, cosine phi sine phi is going to be a constant. So we have cosine phi sine phi times the integral of rho, or the integral of rho cubed, which is going to be rho to the fourth over 4, and I'll move the 1/4 with the cosine over sine. So when I go ahead and evaluate from the row bounds of 1 to 2, we'll get cosine phi sine phi all over 4 times 2 to the 4th is 16 minus 1 to the 4th is 1. So we'll basically get 15 over 4 times cosine phi times sine phi. So now we can go ahead and evaluate the middle integral from 0 to pi over 2, this time with respect to theta. So this entire thing, 15 over 4 cosine phi sine phi, is a constant in this case. So the integral will just be 15 over 4 times cosine phi times sine of phi times theta. Let's go ahead and evaluate from the theta bounds of 0 to pi over 2. So when I evaluate, we'll get 15 over 4 times cosine phi sine of phi, and then times, when I plug in pi over 2 for theta, we'll just get pi over 2, minus when I plug in 0. That will cancel, and so we're left with 15 pi over 8 times cosine phi times sine of phi. So now we can finally get rid of the phi variable by integrating with respect to phi from 0 to pi over 2. Now 15 pi over 8 is just a constant, so the integral of cosine phi sine of phi, now I just have to use u substitution here, so if I said u equal to sine of phi, then du is going to be cosine phi d phi. So rewrite that again. We get cosine phi d phi. And if I isolate d phi, is going to be equal to du over cosine of phi. Now if I substitute that back into the integral, I'll leave 15 pi over 8 outside as a constant, times the integral from 0 to pi over 2 of cosine phi times u, because I made u equal to sine of phi, times d phi, which is du over cosine of phi. Cosines will cancel, and so we're just left with the integral of u du. Now the integral of u is going to be u squared over 2, so we'll get 15 pi over 8 times u squared over 2. Once again, u is sine of theta, so sine squared of theta, or sine squared of phi, over 2. Now if I go ahead and multiply those two, we'll get 15 pi over 16 times sine squared of phi. Let's go ahead and evaluate that from the phi bounds of 0 to pi over 2. So when I evaluate, we get 15 pi over 16 times, we get sine squared of pi over 2. Now sine of pi over 2 is 1, 1 squared is 1, minus sine of 0 is 0, 0 squared is 0. So our final answer is going to be 15 pi over 16.